As we all know, electricity is the flow of electric current within a conductor, which is usually generated via battery cells or an alternator. However, generators are usually used because they provide electric current in commercial quantity. However, in order to generate this electric current at commercial quantity, then there has to be a relative motion between the copper windings and a magnetic field. Thus, electricity is generated in commercial quantity as a result of these interactions. So in order to create this relative movement between them, prime movers are usually used. That is to turn fluid flow into mechanical motion.
And examples of these fluid flows are steam, gas, wind, and water. However, there is a need to use a medium to capture this fluid flow. One of the mediums that is normally used for this purpose is known as a turbine. And the turbine used is designed according to the type of flowing fluid type.
Hydroelectric energy, which is also called hydroelectric power or hydroelectricity. It is a form of energy that harnesses the power of water in motion, such as capturing waterfall to generate electricity.
In the past, people have used this method for millennia. That is, over 2,000 years ago. The Greeks usually used flowing water to turn the wheel of their mill in order to ground their wheat into flour.
In the generation of hydroelectric power, water is collected or stored at a higher elevation and led downward through large pipes or tunnels, usually called penstocks. This is then channeled to a lower elevation. The difference in these two elevations is known as the head. At the end of its passage down the pipes, the falling water causes turbines to rotate. And the turbines in question will turn the shaft of the generators, which will convert the turbine's mechanical energy into electricity. Transformers are then used to convert the alternating voltage to a higher voltage, which will be suitable for long-distance transmission. The structure that houses the turbines, generators, and the pipes or penstocks feed is called the powerhouse.
By design, hydroelectric power plants are usually located in dams that impound rivers, thereby raising the level of the water behind the dam and creating as high a head as is feasible. The potential power that can be derived from a volume of water is directly proportional to the working head. So a high head installation requires a smaller volume of water than a low head installation to produce an equal amount of power.
However, during dam construction, a temporary part is created which is also called a diversion channel. The flowing water is then channeled via this new diverted path and the main part is sealed off, thereby allowing construction to be done on dry land. In this case, the soil and rocks condition is checked, and in a case where the soil appears to be weak or the rock appears to be weathered, the weak spot is cleared, thereby allowing the dam construction to be laid on a solid foundation. After construction, the temporary diversion will be removed, thereby allowing the water to be collected and stored before it will be channeled to the turbine via the penstock.
Let's look at it in terms of water discharge to and fro from the dam. Hydroelectric discharge, which is also referred to as flow rate, is usually denoted by Q. It is the volume of water that passes through a hydroelectric power plant per unit time. Thus, the unit for flow rate is meters cubed per second. Understanding the flow rate of the stream or river used for a hydropower generation plant is vital in predicting the available hydropower energy. This, along with the head drop of the stream or river, are the two values necessary to calculate the available power. Flow rate simply represents the volume of water that can be captured and then redirected by a dam to flow across a turbine generator in order to move it and generate electricity. The larger the flow, the more energy that is available to be converted to electricity.
Both a high flow rate and a high head are not necessary for a hydroelectric power plant to be viable. If there is a high flow rate, the head doesn't need to be as high as the sheer amount of water flowing through the dam before it will be sufficient to move turbines. Conversely, if the water is falling from a large height, it isn't as important for a large volume of water to flow to the turbines.
That said, before we go into some calculations, let's have a look at the following terms. Power is the rate of producing energy. Power is measured in watts or kilowatts. Energy is what is used to do work and is measured in kilowatt hours or megawatt hours. In simple terms, the maximum hydropower output is entirely dependent on how much head and flow is available at the site. So using these equations, P equal M multiplied by G multiplied by H net multiplied by eta, where P is measured in watts, meter is mass flow rate in kg per seconds, G is the gravitational constant, which is 9.81 meter per second square. H net is the net head. This is the gross head physically measured at the site, less any head losses. To keep things simple, head losses can be assumed to be 10%, so H net equal H gross multiplied by 0.9. Eta is the product of all of the component efficiencies, which are normally the turbine, drive system and generator. For a typical small hydro system, the turbine efficiency would be 85%, drive efficiency is 95%, and generator efficiency is 93%. So the overall system efficiency would be 0.85 multiplied by 0.95 multiplied by 0.93 equals 0.751, which is equivalent to 75.1%. Therefore, if you had a relatively low gross head of 2.5 meters and a turbine that could take a maximum flow rate of 3 meter cubed per second, the maximum power output of the system would be: first, convert the gross head into the net head by multiplying it by 0.9. So H net equal to H gross multiplied by 0.9 equal to 2.5 multiplied by 0.9 equal 2.25 meter. Then convert the flow rate in meter cubed per second into liters per second. That is by multiplying it by 1000. So 3 meter cubed per second equal to 3000 liters per second. Again, it is important to remember that 1 liter of water weighs 1 kilogram. So meter is the same numerically as the flow rate in liters per second. In this case, it is 3000 kilograms per second. Now we calculate the hydropower power. Power equal mass flow rate multiplied by gravitational constant, multiplied by net head, multiplied by component efficiencies, equal to 3000 multiplied by 9.81, multiplied by 2.25, multiplied by 0.751, equal to 49,729 watt, or 49.7 kilowatts.
Now, we can calculate another hydropower site with high head, where the gross head is 50 meters, and the maximum flow rate through the turbine is 150 liters per second. In this case, H net is equal to 50 multiplied by 0.9, which equal to 45 meters, and the flow rate in liters per second is 150. Hence power equal mass flow rate multiplied by gravitational constant, multiplied by net head, multiplied by component efficiencies, which is equal to 150, multiplied by 9.81, multiplied by 45, multiplied by 0.751, all equal to 49,729 watts, or 49.7 kilowatts.
What is interesting here is that for two entirely different sites, one with a net head of 2.25 meters and the other 45 meters, can generate exactly the same amount of power because the low head site has much more flow when compared to the high head site with just 150 liters per second. This clearly shows how the two main variables work when calculating hydropower output from a hydropower system. These variables are the head and the flow rate, so power output can be said to be proportional to the head multiplied by the flow.
It is on this note that there are two main types of hydropower turbines. These are reaction and impulse turbines.
The type of hydropower turbine selected for a project is based on the height of the standing water, or the volume of the water over time at the site.
Other deciding factors include how deep the turbine must be set, turbine efficiency, and cost.
So it can be said that a reaction turbine is a turbine that generates power from the combined forces of pressure and moving water. A runner is placed directly in the water stream, allowing water to flow over the blades rather than striking each individually. Reaction turbines are generally used for sites with lower head and higher flows.
The two most common types of reaction turbines are Francis and propeller turbines, or Kaplan turbine, which is the adjustable version of the propeller turbines.
The Francis turbine was the first modern hydropower turbine and was invented by British-American engineer called James Francis in 1849. A Francis turbine has a runner with fixed blades, which is usually 9 or more. Water is introduced just above the runner and all around it, which then falls through, causing the blades to spin. Besides the runner, the other major components include a scroll case, wicket gates, and a draft tube. Francis turbines are commonly used for medium to high head situations, and although they can also be used for lower heads as well. Francis turbines work well in both horizontal and vertical orientations. Kaplan turbine, on the other hand, is a type of water turbine that converts the kinetic energy of water into mechanical power. Invented by Austrian engineer called Victor Kaplan in the early 20th century, this turbine is specifically designed to harness the power of low to medium head water sources, making it ideal for locations with moderate water flow. Its distinguishing feature lies in the adjustable blades, or propeller, which can be rotated to optimize performance under varying flow conditions. This flexibility allows the Kaplan turbine to deliver exceptional efficiency and power generation across a wide range of water flow rates.
While impulse turbines are turbines that generally use the velocity of the water to move the runner and discharge at atmospheric pressure. During operation, water stream hits each bucket on the runner. With no suction on the downside of the turbine, the water flows out the bottom of the turbine housing after hitting the runner. An impulse turbine is generally suitable for high head, low flow applications. The two main types of impulse turbines are Pelton and cross-flow turbines.
The Pelton turbine was invented by an American inventor called Lester Allen Pelton in the 1870s. A Pelton wheel by design has one or more free jets discharging water into an aerated space and impinging on the buckets of a runner. Pelton turbines are generally used for very high heads and low flows. Draft tubes are not required for an impulse turbine because the runner must be located above the maximum tailwater to permit operation at atmospheric pressure. On the other hand, a cross-flow turbine was designed by Anthony Michel, an Austrian engineer, in the early 1900s. Later, Dana Bonki, a Hungarian engineer, improved upon it, and it was improved even further by German engineer Fritz Asperger. A cross-flow turbine is drum-shaped and uses an elongated, rectangular section nozzle directed against curved vanes on a cylindrically shaped runner. It resembles a squirrel cage blower. The cross-flow turbine allows water to flow through the blades twice. On the first pass, water flows from the outside of the blades to the inside, while on the second pass, water goes from the inside back out. A guide vane at the entrance to the turbine directs the flow into a limited portion of the runner. The cross-flow turbine was developed to accommodate larger water flows and lower heads than the Pelton can handle.
So based on the earlier calculations, It can be said that the low head site would need a physically large Archimedean screw or Kaplan turbine inside a turbine house. And the size must be large enough in order to be able to physically discharge such a large volume of water with a relatively low pressure across it. While the high head site would only need a small Pelton or turbo turbine the size of a fridge. That is because it only has to discharge 5% of the flow rate of the low head system under a much higher pressure.
Now that we have understood how fluid flow works in relation to the turbine design, we can now look at the working flow of hydropower plants. After the moving water has been dammed, water from the reservoir flows from the intake through the gate to the penstock and then spins the blades in a turbine, which in turn spins a generator via the runner, and electricity will be produced in commercial quantity afterward.
Again, the reason why the intake is designed that way is to prevent debris from being collected at the base, thereby blocking off the flow path to the penstock. While the penstock is usually constructed using a steel line. The reason why steel line is used is to prevent weathering in the long run. Also, within the turbine's hollow casing, there is a governing mechanism that is meant to regulate the amount of water that flows to the turbine. That is, when the power demand is at peak, more water will flow to the dam, while, and likewise, when the demand is low, less water flows to the turbine. Finally, in terms of the generator design, sometimes the generator might be made of magnets, or it can be wound with some set of copper wire which will be further connected to an exciter. Again, the aim is to achieve the relative movement between a magnetic field and the conductor windings. Hence the reason why the electricity is generated as the turbine begins to rotate and turn the generator rotor when water begins to flow through the blade of the turbine. The generated electricity will be further connected to a transformer, which will further step the generated voltage to a very high voltage before it is transmitted to the grid. And that is it on today's series. In the next series, we will be looking at transmission lines. The way many power stations are interconnected in parallel will be looked at. So until then, peace.